cinematic deep dive into the incandescent light bulb, the spark of genius, the thousands of failed filaments, the race against rival inventors, and the night Menlo Park glowed to banish darkness forever. Today, we step back to the late 19th century, an era of flickering gaslight, steam-driven factories, and the sudden, blinding birth of the modern electrified age. In a world defined by boundaries, some stories cannot be contained by borders. This is Of the World, Chronicles of Innovation. For centuries, the human day was defined by the rising and setting of the sun. Night was a time of forced rest or hazardous darkness, illuminated only by the dim, smoky flicker of candles, oil lamps, or gas jets. Gaslighting was expensive, smelly, and a constant fire hazard that consumed oxygen, blackened walls, and caused frequent explosions in homes and public spaces. The quest for a clean, safe, and cheap source of light was the holy grail of the industrial age. While early scientists had demonstrated that electricity could produce light through arc lamps, these were too bright, noisy, and dangerous for indoor use, suitable only for streetlights or large factories. The world was waiting for a gentle, domestic glow. We begin our story in the winter of 1876, in a quiet New Jersey hamlet where one man promised to solve this riddle once and for all, transforming the way humanity lives and works. In the autumn of 1876, Thomas Alva Edison established the world's first industrial research laboratory in Menlo Park, New Jersey. This was not a solitary inventor's workshop, but a structured invention factory, bringing together draftsmen, engineers, chemists, and machinists under a single roof. Edison's goal was not merely to invent a light bulb. Others had already created electric arc lamps and rudimentary incandescent burners, but to create a complete, practical, and commercially viable system of electric lighting that could replace gas inside homes and offices. This required a bulb that could burn for hundreds of hours using a small amount of current, a feat many contemporary scientists and academic physicists deemed mathematically impossible. Edison realized that to make electric light practical, he needed a high-resistance filament that would require less copper wiring to deliver electricity, thus keeping the system economical. While skeptics mocked his ambitions, Edison and his team of muckers set to work, designing generators, meters, cables, and sockets from scratch. The laboratory itself became a hub of constant 24-hour activity, fueled by caffeine, tobacco, and the relentless drive to harness the power of the electron. To achieve a high-resistance filament, Edison knew he needed a perfect vacuum inside the glass bulb. If any oxygen remained, the filament would burn up instantly when heated. He acquired the newly invented Sprengel air pump, a device that used falling mercury to extract air to a degree never before possible. With this pump, Edison's team could produce a vacuum of 1/1,000,000th of an atmosphere. In this extreme vacuum, materials that would normally burn in seconds could survive for hours. The search for the right filament material became a legendary quest. Edison and his assistants tested over 6,000 organic substances, including cardboard, paper, carbonized threads, cork, fishing line, and even hair from the beards of his assistants. They carbonized these materials by heating them in closed ovens, transforming them into fragile strands of pure carbon. Each material was carefully cataloged, mounted on platinum support wires, sealed inside a glass bulb, and connected to the electrical generators. Most failed instantly, glowing brightly for a fraction of a second before snapping into dust. Yet Edison refused to give up, viewing each failure as valuable data that brought them closer to their goal. The breakthrough came on October 21st, 1879. Edison's chief chemist, Charles Batchelor, carbonized a piece of ordinary cotton sewing thread. They carefully mounted the thread, evacuated the bulb using the Sprengel pump, and applied the current. The filament began to glow with a soft, warm light. Edison and his team sat in silence, watching the bulb. Hours passed, and the light remained steady. The bulb continued to burn for 13.5 hours before the glass cracked and air entered, destroying the filament. This successful test proved that carbonized organic fibers were the key to practical incandescence. The team celebrated, but Edison immediately pushed them to improve the design. He sent scouts across the globe to search for the perfect carbon source. They traveled to South America, the Caribbean, and Asia, collecting wild plants and fibers. In Japan, explorer William Moore discovered a specific species of bamboo. When carbonized, this bamboo filament proved to be incredibly durable, allowing the bulbs to burn for over 1,200 hours. This bamboo filament became the standard for Edison's commercial bulbs for the next decade. But inventing the bulb was only half the battle. Edison faced fierce patent litigation and commercial competition from rival inventors on both sides of the Atlantic. In Great Britain, physicist Joseph Swan had developed and patented a carbon filament lamp independently, even demonstrating it before Edison. Rather than waste fortunes in protracted court battles that could ruin both companies, Edison and Swan merged their British operations into the Edison and Swan United Electric Light Company, known popularly as Ediswan. In the United States, Edison fought off legal challenges from Westinghouse, Hiram Maxim, and the United States Electric Lighting Company. These battles established the critical importance of patent strategies and intellectual property in the corporate industrial age, proving that the business of innovation was as competitive and cutthroat as the science behind it. Edison's ability to protect his patents allowed his company to dominate the American market, securing the capital needed to fund his next grand ambition, the electrification of the world's cities. To make the light bulb useful, Edison had to build the infrastructure to power it. On September 4, 1882, he switched on the Pearl Street Station in Lower Manhattan, the world's first commercial central power plant. Providing direct current electricity to a 1 square mile district, it illuminated 85 buildings, including the offices of the New York Times and the financial houses of Wall Street. The modern utility grid was born. However, Edison's direct current system, which could only transmit power efficiently over a distance of 1 mile, soon faced a major technological challenge. Nikola Tesla and George Westinghouse advocated for alternating current, which could be stepped up to high voltages and transmitted over hundreds of miles before being stepped down for safety. This triggered the bitter war of the currents. Edison waged a public relations campaign against alternating current, even demonstrating its dangers, but the superior efficiency of alternating current ultimately won, establishing the standard for the global grids we rely on today. The incandescent light bulb did far more than banish darkness. It decoupled human activity from the natural cycle of the sun. Factories could run night shifts, extending industrial productivity, and cities became vibrant, safe, and active nocturnal hubs. It changed the architecture of homes, the nature of work, and the very rhythms of human sleep. Before electric light, people slept in two distinct phases, divided by a period of quiet wakefulness. The introduction of reliable artificial light merged these phases into a single, continuous block of sleep, permanently altering human biology. The light bulb also created a new nocturnal economy, allowing theaters, restaurants, and shops to operate late into the night. It transformed the home, replacing the flickering, hazardous flames of gas lights with a clean, steady glow that did not consume oxygen or release soot. The simple bulb became a symbol of progress, intelligence, and modern civilization. Today, as we transition to highly efficient light-emitting diodes, the warm glow of Edison's carbon filament remains the universal symbol of a brilliant idea. The legacy of Menlo Park, the birth of organized research and development, continues to shape how modern technology is created. Edison proved that innovation is not just about isolated sparks of inspiration, but about systematic, collaborative effort and rigorous testing. The wheels of progress keep turning, and the technologies we use continue to evolve, but the core principles of scientific inquiry and engineering design remain unchanged. The spark of genius never fades. The future is always being written. This has been Of the World, Chronicles of Innovation. The spark of genius never fades. Keep creating.